Hello and welcome back to Calculus 2 Notes. We're going to start out section 8.2 now, talking about series. So basically, we looked at sequences in the last section, and there are ways to build new sequences out of sequences you already have. In particular, if you take each of the terms in the sequence and you start adding them up as you go along, you get a new sequence which is called a series. It's like a sequence of partial sums that you get as you add up the original sequence. And this is going to be one of the main things we study for the next few weeks. And it turns out that series play a very powerful role in calculus. And we're going to see how they connect to that stuff later on. So you can look at a sequence, which we're going to label as S sub n, the series or the sum of adding up terms of a particular sequence A sub n. So our third entry in our series is going to be the sum of the first third entries in the sequence. So notationally, we write this as S sub n equals the sum from I equals 1 to n of A sub I, right? So my S sub 3 here means I'm adding up A sub 1, A sub 2, A sub 3. And we call this sequence the sequence of partial sums for the series A sub n. And I want you to go ahead and do exercise 1. And the idea here is you're going to be not just writing out the terms of the sequence, but actually adding them up and letting me know whether you think this thing's going to converge or diverge. So pause the video now, try that on your own, and then unpause it when you're done. Okay, so our A sub n here, if we look at just the first 5, it's going to be 1, 2, 3, 4, 5. So our sequence S sub n for, or our series S sub n, our first entry is just going to be 1, but then we add 1 plus 2 to get 3, and then we add 1 plus 2 plus 3 to get 6. And what's really happening is when I go from this from the 6 to the next one, I'm really just adding the next term. This next one's going to be 10, and then 15, and it's going to keep going. And that totally looks like it's going to diverge because it's increasing, and it's increasing rapidly. So yeah, this is definitely going to diverge. These, by the way, are called the triangle numbers, which I can tell you about at some later date if you care. Here, our A sub n, this is going to be 1, 1/2, 1/3, 1/4, 1/5. And our sequence of partial sums for this is going to be 1, and then 1.5, or I guess 3/2 might be nicer. When I add 1/3 to that, I've got to get common denominators, and it comes out to being 11/6. Then next I get 25 over 12, and then 137 over 60. And this one's kind of hard to say. I mean, we start at 1. Here we're just a little bit over 2. It definitely seems like it's increasing, but the rate at which it's increasing is getting smaller and smaller each time. So I might guess that this one converges, but it's kind of hard to say. Our next one here, I'm just going to go straight to the sequence of partial sums. My first one is 1/2, and then next I'm going to have 1 over 2 squared, which would be 1/4, plus 1/2 will give me 3/4. Then I add in a 1/8, and that will give me 7/8, and then I'll end up getting, 15 16ths, because I'll add in a 16th. Then I add in a 32th, and I get 31 over 32. This looks to me like it's going to converge to 1. And the reason here is that my partial sums, they're increasing, but they're never really going to get above 1. And it seems like that's what they're going to get closer and closer to. We don't have the ability to prove yet that will converge. Although I guess what's really going on here is this is our sequence of partial sums. We can actually do a calculation. I'm not going to do it here, but we can show that it's equal to 2 to the n over 2 to the n minus 1. And if you think through what that equals, you can convince yourself that that will in fact converge to 1 as n gets larger and larger. All right, so a sub n here, each of these terms, we're just adding on another 9 in the decimal expansion. That's going to get closer and closer to 3. So our s sub n, it's going to be like 2.9, and then we're going to get all these like 5.89, 8.889, 11.8889, and 14.8889, etc. And this definitely looks like it diverges. And the reason here is our original sequence is converging to 3. If I keep adding up 3's, I'm just going to get bigger and bigger and diverge. All right, and our last one here, our first entry is 1. We add 0 to 1, we get 1. Add negative 1 to that, we get 0. Add 0 to 0, we get 0. Add 1 to that, we get 1. Add 0 to that, we get 1, etc. And this is just going to bounce back and forth between 1s and 0s. So this is going to diverge. It doesn't get like ridiculously large, but it's never going to settle down on either a 0 or a 1, so it will not converge. All right. Oh, exercise 2. Now that we know our results from exercise 1, can we make any conclusions about the relationship between the convergence of the original sequence and the convergence of the sequence of partial sums? So pause your video now and see if you can make any conclusions or summarize what you found in the first exercise there. So some of the things that I notice about this is if the original sequence converges, the s sub n may or may not converge. So our example here is letter B, that this sequence converges to 0. Letter C, this sequence converges to 0. Letter D, this sequence converges to 3. Letter E, it doesn't converge at all. So these 3 all had convergent sequences. One of them I wasn't sure if it converged. One of them I thought did converge, and the other one diverged. So just because the original sequence converges, your partial sums may or may not converge. If your original sequence a sub n diverges, then your sequence of partial sums will also certainly diverge. At least that's what we've seen so far. Our letters E and A, so E and A, those were both divergent sequences, and both of those series also diverged. So this sequence of partial sums is the basis for what we're going to cover in Chapter 8. In particular, we're interested in whether or not a sequence of partial sums diverges or converges, and if it converges, what it converges to. And if you take the limit as n goes to infinity of a sequence of partial sums, you get something called a series, which we usually denote with sigma notation that looks like this lovely thing. Sum I equals 1 to infinity of a sub I. That notation should look familiar to you because it looks pretty similar to stuff we used for Riemann sums and taking the limit of Riemann sums as they go to infinity. So a series has 2 built-in sequences. The sequence a sub k that we're sort of adding up, and then the sequence of partial sums, S sub n. And depending on what we're dealing with, the sequence of, I guess, the sequence that we're adding up is often going to tell us information about what we get for the sequence of partial sums. In particular, yeah, the properties of the original sequence, that's the A sub n, and what that tells us about convergence or divergence of the sequence of partial sums. So let's start with a geometric series. So a geometric series has the following form. I'm going to do this in purple. You're adding up some number A, and then each successive thing that you add up, you're multiplying A by some ratio R. And that goes on forever. So it looks like this: sum from n equals 1 to infinity of A times R to the n minus 1. So if I plug in 1 for my n up here, I'll get R to the 0, which would turn that into a R to the 0 would just be 1, and I'd just be left with A as my first term. If I plug in n equals 2, I get A times R, that's my second term, and it goes on forever. You can also write it the following way. You can start your n at 0 and have this be AR to the n. This looks a little bit nicer because we don't have to deal with the n minus 1 in the exponent, but we're starting at a different starting number. And just be aware that these won't always start at I equals 1 or n equals 1. They can also start at 0 or anything else. This first term in the series we call A. That's our initial term, is often the thing we call that. And then we're multiplying by R, which we call the common ratio. So example 4 basically just gives us an example of a couple of these, what they look like. So 1 over 3 to the n, we could rewrite this if we wanted it to look like this thing right here. We could say that it's a sum from n equals 0 to infinity of 1 times 1 over 3 to the n. And actually, I'm going to rewrite that 1 over 3 to the n. I'm going to call it 1 over 3 parentheses to the n. So here, this is my A, that's my initial term. And the 1/3 here is my R, right? So that's my R to the n power. And if I wrote out the first few terms of this, plug in n equals 0, you get 1 over 3 to the 0 is just 1. So this is 1 plus 1/3 plus 1/9 plus 1 over 27, etc. This one looks a lot more like that form right there. It kind of looks like my A would be 1/2. The problem is that this 3 to the n here is not a 3 to the n minus 1. If we wanted to make it look like that, we'd have to modify it, and we would have to, I guess, factor out a 3. So in sum to infinity, n equals 1, 1/2 times 3 to the n minus 1. So 3 to the n, this whole thing right here is 3 to the n, because this is like a 3 to the 1. And when I multiply those two together, I'll add the exponents, and the 1 and the -1 will cancel. And then I can combine these two to get sum to infinity, n equals 1 of 3/2 times 3 to the n minus 1. And that will now look exactly like the form that I have here. Realistically, though, if you're dealing with a geometric series, oftentimes it's easiest just to start writing out the terms. And so here A equals 3/2 and R equals 3. But if I thought this was a geometric series, I could also just start writing out the terms. I plug in n equals 1, I get 3 halves as my first term, plug in n equals 2. I get 9 halves, plug in n equals 3, and I get 27 over 2, etc. And then I say, oh, look, here, my first term, that one right there, is 3 halves. I call that a. And then when I go from here to here, I'm multiplying by 3, and from here to here, I'm multiplying by 3. So my common ratio is 3. If you just start writing out the terms, you can often figure out what the a and the r are without necessarily fiddling around with putting it in, the exact correct form. We'll stop there.